Welcome to the third lecture in our Module 7 on probability distributions, sampling distributions, and the central limit theorem. And so here in this third lecture, I'm going to focus on sampling methods, sampling distributions, and the central limit theorem. The first two lectures we talked about probability distributions for variables, whether they be discrete or continuous. And so here we're going to start talking about sampling distributions. So so we have populations and we have samples, right? And the population is the entire collection or set of items that have something in common that we're interested in. And the sample is a subset of that population. And it's selected in such a way as to hopefully be representative of the larger population. And what we want to do is make inferences or generalize from the sample to the population. That's our goal here. And so let's start with the sampling frame. So a definition of the sampling frame is the actual set of units from which a sample will be drawn. And so this is like a hypothetical list that contains every member of the population from which a sample will be selected, because you got to select the sample somehow, right? So you need the frame is the first thing that you need to have straight. So why sample? Well, maybe you're thinking, why am I taking the statistics course? Anyway, so why do we sample? Samples may be studied more quickly than the general population, because samples are smaller than the general population. They can be studied less expensively. It's going to take a long time to collect data on the entire population. Think of how long it takes to collect the US Census and then to process all that data. We don't want to wait, years and years and years before we answer our business question, and your boss probably isn't going to want to wait that long either. So you're going to want to generate a sample. Interestingly, depending on how you select the sample, your sample results may end up being more accurate than results from an entire population and help actually reduce some of the heterogeneity depending on your sampling method. So there are four types of probability sampling, and this is the kind of sampling that we're interested in. The first is simple random sampling. Then we also have systematic sampling, stratified sampling, and cluster sampling. In simple random sample, every subject has an equal probability of being selected. Interestingly, you can use Excel for selecting a random sample. So you enter that command equals ran between in brackets 1, 100, and that'll give you a random number between 1 and 100. You do that a bunch of times and you're going to get a bunch of random numbers, and then you can just pick people off your sampling frame like you were giving them lottery tickets. Okay, so a systematic sample, similar to a simple random sample, it involves randomly selecting elements from an ordered sampling frame. The difference is that you have a random starting point called a seed. You could generate that seed using that Excel function that I used before. It's going to be just some random number. And then because your entire population is ordered from 1 to whatever your population size is, you take that seed and then select every kth, which is just to say some number, such as every 10th or every 100th member from the total population, starting with that original random number seed. This is typically how random samples are actually generated. There's also a stratified random sample, sometimes called proportional or quota random sampling. It involves dividing the population up into homogeneous subgroups and then taking a simple random sample in each subgroup. This is because you might want to make sure you get enough representation in each subgroup. So you could use age, gender, socioeconomic status, religion, nationality, educational attainment, etc. to divide your population up into subgroups. A cluster sample involves a form of probability sample, but it's where the respondents are drawn from a random sample of mutually exclusive groups referred to as clusters within the total population. So this is really random sampling at the group level. For instance, neighborhoods. You might randomly select, if you live in St. Louis, I don't know how many neighborhoods there are here, but say you randomly selected 10 neighborhoods out of however many there are. And then typically within the cluster, everyone would be included in the sample. There's also non-probability sampling, referred to as convenience sampling, also known as taking what you can get. So in this, you don't have any probability of whether, you can't know the probability of whether a given subject from a population would be selected. And so there's going to be selection bias in non-probability sampling because it's not probabilistic. So for instance, an example of this would be patients who show up in an emergency department on a Saturday afternoon and agree to take your survey. That would be an example of a convenience sample. We can't really do any inference from a convenience sample. So let's talk about sampling distributions. Basically, a sampling distribution is a distribution of a sample statistic. And really the only sample statistic that we're going to be talking about sampling distributions for is the mean. And so the sampling distribution of the mean is a theoretical distribution of all possible values of the mean taken from all possible samples of a given size obtained from the population. So what on earth does that mean? Let's talk about an example. Suppose we're interested in the effects that growing up in the 1990s has on the amount of time Americans spend watching reality television. Imagine that we were then able to take an infinite number of samples of 10 Americans. So each sample size has 10 Americans in it. So we sample and sample and sample. Now we have an infinite number of sets of 10 scores. If we were to take the mean for each of those samples, now what we would have is an infinite number of means. And we could actually then plot those means on a probability density curve based on their frequency. And once they're plotted, that's all a sampling distribution of the mean is. As you can probably tell, this is a hypothetical distribution. So what? Why should you care? The sampling distribution of the mean is used for hypothesis testing. And guess what? We're going to be talking a lot about hypothesis testing in the next couple of modules after this one. It's one of the most important aspects of any statistics class. So we take a sample of people, for example, these people who grew up in the 1990s. We want to know if our sample is different from the regular population. So the entire population, which might exhibit the normal level of reality television watching. And we want to know if our sample belongs to some different population, perhaps that of excessive reality TV watchers. So we take our sample mean and test where it would lie on our regular population distribution. And then we make a decision about whether or not there's a big enough distance between our sample mean and the population mean. And if the difference is large enough, then we infer that these individuals likely did not come from the regular population and came from some other population. Population of excessive reality television watchers, and after that we would probably further infer that if we had enough controls that growing up in the 1990s exerted a causal effect on excessive reality television watching. So let's talk about the sampling distribution of the mean. The sampling distribution of the sample mean is normally distributed if the population distribution is normal. So if the parent population is normal, then the sample mean is normally distributed. It's indicated by x bar, and it's equal to mu, the population mean. And it has a variance of sigma squared, which is the population variance, divided by n, which is the sample size. So as you can see, as your sample size increases, your variance decreases. And you want low variance. So the bigger your sample size, the better. The variances of sampling distributions are smaller than the variance of the population distribution because we're dividing it by n, and decrease as the sample size increases. Okay, so there's good news here. And let's talk about the standardized sample mean. We can actually standardize the sample mean just like we did in the previous lecture for the random variable x, because the sample mean is also itself a random variable. And then we use the standard normal table to look up its probability. The mean of the standardized sample mean is 0 and the variance is 1 because it's on the standard normal distribution. So if the population is normal, then we compute this variable z, which is a standard normal variable that we learned how to compute in the second lecture, except the difference being here that our sample mean itself is now the entity x transform. So you can see the formula there in the left-hand corner. Z is equal to our sample mean x bar minus the population mean mu divided by the population standard deviation. It's in the denominator there, which is itself then divided by the square root of n, the sample size. We can also compute a standard error for the sample mean, which is equal to the population standard deviation divided by the square root of n, the sample size. Okay, I'm briefly going to mention the t-distribution here. When the population, because you might say, well, hey, what if we don't know the population standard deviation? That's the whole reason why we're sampling, right? Of course. So when the population standard deviation is unknown, the population standard deviation can be estimated by the sample standard deviation S. And when S is used, then the sampling distribution of the mean changes and it follows a t-distribution instead of the standard normal distribution. You can see the formula for it there. Don't worry about it yet. We will be covering this in extensive detail in modules 8 and 9. Okay, so lastly, let's talk about the central limit theorem. No statistics course would be complete without discussing the central limit theorem. The sampling distribution of the mean with repeated random samples has these three properties. One, we already discussed this, the mean of the sampling distribution of x bar, which when you think about it, the mean of the sampling distribution is really the mean of the sample means. This is equal to the total population mean mu. Secondly, the standard deviation in the sampling distribution of x bar, our sample mean, is equal to the standard deviation of the population, denoted by sigma, divided by the square root of the sample size n. We discussed that already. Thirdly, this is the point that is very important that I really want to emphasize because it's very good news. Regardless of the shape of the original population distribution, if your sample size is big enough, sufficiently large that is, the sampling distribution of the mean is approximately normally distributed. So your original population may not be normal at all. It might be a really screwy distributed variable. As long as your sample size is big enough and you're sampling randomly, the sampling distribution of the mean, the sample mean, is normally distributed. So, and then we can use our handy standard normal table to look it up. So that's really good news. So you might say, well, what is a sample size that is big enough? And the good news is a sample of at least 30 is sufficiently large. And so that's not too, that 30 is not too difficult to get, right? A sample size of 30 is not so big that it's going to be impossible to get. So this is really great news. Whoever came up with this theorem is pretty smart, and it's going to help us a lot in the rest of this class. Okay, so what does the standard normal distribution look like? So this is kind of like an empirical rule for normally distributed data. And as you can see here, you see the standard normal distribution ranging from plus to minus 3 standard deviations, which would also be plus or minus 3 on the z-score table. 50% falls in one side of the mean of mu there, which would also be equal to 0. 50% falls on the left side of the mean. Interestingly enough, 68% of observations lie within plus or minus 1 standard deviation of the mean. 95% lie within plus or minus 2 standard deviations of the mean. and 99.7% lie within plus or minus 3 standard deviations of the mean. And as we'll see in the next modules, these values of 95% and 99.7% are often used for conducting hypothesis testing.